has very frequent periods of activity. In 2002, the calendar year alone, 3 of these volcanoes erupted that we know of. So it is actually a very, very active volcanic arc. And it's very common for having these ephemeral islands, islands that pop up to an eruption, and they'll last a few months, days, sometimes maybe a year or two before they get washed away. So, quite often you see in the media the latest new island in the world, and chances are it will appear here in this Tofua volcanic arc. And just if we zoom in a bit to look at where this volcano lies in terms of the context of the main island of Tonga. The main island of Tonga is Tonga Tapu, which you see there. The volcano that's known as Hunga Tonga Hunga Ha'apai actually has a single edifice that lies about 50 kilometres to the north of the capital, Nuku'alofa. So it's actually very close to very high populated areas. And the reason why it's called Hunga Tonga Hunga Ha'apai is because it's actually 2 islands. And so these volcanoes are named if there is an island, in which case there are 2 of them. If the submarine, it's named by geologists, and I've got to say, geologists, well done, you're really boring, because they're called imaginative things as Volcano 3, Volcano A, nothing fancy. So the reason why it's called Hunga Tonga Hunga Ha'apai is it started off as 2 islands, which is a remnant of a rim of a larger caldera on a large edifice called Hunga Volcano. November 2014, it started 2 islands, but in 2015, a new volcano started between them, and eventually grew and actually joined the 2 islands together. Now, because in Tongan naming convention, volcanoes are named after the islands, imaginatively, we put a hyphen between them, and the volcano is called Hunga Tonga Hunga Ha'apai. But make no mistake, this is actually part of a larger single edifice that in scientific literature we are now calling the Hunga volcano. That's in the wrong order. Let's start with this one. This will start, this is, be patient, it will start. So this is a shot taken on January the 14th. So it's 24 hours before the Big Bang. This is taken by the Tongan Geological Services. It was taken from a vessel that was at the limit of the human exclusion zone of 5 kilometres from the volcano. They used a drone. I find this footage incredibly mesmerising, just watching the plumes come out and the lightning strikes. But I like what you're going to see now, which is this lovely Sertzian eruption happening. It rises up about 1,000 metres into the air, but then you get column collapse, and you get this lovely pyroclastic flow coming out the end. And this sort of volcanic activity, we at the time, in terms of what we expected for this volcano, really represented the limit of its volcanic experience. In terms of health and safety, this is the exclusion zone. In terms of risk management, we thought this is a safe that we could approach and be completely safe. And that's kind of what all the leading health and safety regulations said, and all the textbooks say about these sorts of stratovolcanoes. That's the same sort of health and safety exclusion zone that we apply to Whakaari Right Island or Ruapehu. But actually, 24 hours later, we actually showed how completely wrong that was, because this happened. So in terms of what we thought we knew as scientists about these exclusion zones, if that boat was there when that happened, that would have been vaporised. We followed this up with a Tonga voyage, and part of the plan I had to do was actually do a health and safety assessment and work out what safe zones were, and actually had to use an atomic bomb calculator to work out blast wave pressure points to find out actually at what point would it be survivable from that particular blast. And the answer was, if you're in a steel vessel that was protected from the outside 20 kilometres. So 20 kilometres you would have survived. If you're on the deck 20 kilometres away, you would have had many serious injuries. So it was truly a massive, massive explosion. And it kind of redefined what we thought that we knew about these stratovolcanoes should behave and should act in terms of when they erupt. And actually the tsunami, I'm not going to talk about the tsunami too much. I'm not going to put any more slides in it, but the tsunami is nuts. So there's some really good work that's done by Emily Lane in Christchurch NIWA Christchurch, and she was telling me that there's actually two tsunamis. I guess you probably already knew this, but in the far field, there's something called a meteo tsunami. So the far field is everywhere that the tsunami that hit New Zealand, Australia, Japan, Peru, that killed people, California, Alaska. At every point around the Pacific, that wave was exactly almost exactly 1.5 meters. It didn't matter how far away you were from the blast center, the wave height was always exactly the same. And its arrival times were incredibly fast. So something really bizarre happened by that blast. And actually what drove that blast was, if I switch that and I play this, ignore the cloud, but watch the blast wave generate from it. You can actually see the blast wave generate. And that pressure wave, that air pressure wave, actually drove the meteo tsunami. As that wave expanded at over 1,000 kilometres an hour, it pushed surface water with it. And that surface water pushed by that blast wave is actually what generated the tsunami in New Zealand and around the Pacific. And what was critical about that is it didn't trigger any tsunami alert systems because it's not a traditional tsunami. We think tsunami is some seafloor displacement, and you have this column of water pressure that's moving. Didn't happen. This is just surface water being pushed, and in every case, it was 1.5 meters high. We know through the dark buoy messages and some OBS instruments that were done in Japan, the pressure wave was detected, but it didn't trigger the alert systems. What's cool about this tsunami wave, if we look at the simulation of the atmospheric blast wave, it actually pushed water in the Caribbean. It actually generated a 10 to 20 centimetre high tsunami in the Caribbean. The Caribbean sloshed like a bathtub, backwards and forwards. And there was an actually detected tsunami wave in Europe. It's truly a global event, this blast wave. So that's the far field of the tsunami. In the near field, things get really complicated. Hopefully this will work. No, it's not going to work. In the near field, it got really complicated because we know that there were tsunamis. We saw the pictures of the tsunamis that hit Tonga Tapu. We know that in some places waves reach 20 meters high. We actually know that because NIWA weather stations, so a 20-meter high elevation, switched off. We knew exactly what time it happened. But yet within a kilometre away, the wave height was only 5 meters. So there's something really weird is happening in the near field to the tsunamis. It wasn't just a giant wave. What we think has happened in the explosions, that wasn't just one big event, but probably multiple events. And that was creating multiple waves. And we also think that the volcano was inflating and deflating without an eruptive sequence. And these were also generating tsunami waves. And these multiple events are creating anti-waves and syn waves that are just creating these massive peaks. And that would explain sort of the wave sequence that we actually saw on land. Some other cool, interesting things that came out. These papers came out at AGU when I presented this information in AGU. Tonga this particular eruption had the highest ever plume ever recorded. Now, at the time we first looked at this, end of last year, the height of the plume was 57 kilometres high. So a standard Plinian eruption goes to 20 kilometres, hits the stratosphere, and the stratospheric winds whip the top up, creates like an umbrella. This one actually had two umbrella clouds that actually reached through to the stratosphere and flattened out. And then we think there was a second explosion that was even bigger that punched through the stratosphere right into the mesosphere and created a second cloud at 57 kilometres high. And the latest result we've got from NASA is that they've actually got vapor droplets and aerosols in outer space. This is the first time ever that a volcanic eruption on Earth has pushed material into outer space. I mean, it truly was an absolutely outstanding event. And we don't actually know why, because the things that drive cloud height is either going to be heat and velocity. And we know that these stratospheric heights and mesospheric heights, satellites measure them at about minus 40 degrees centigrade. So they're not hot. So the only thing that can actually push these clouds so high is just the sheer velocity of that explosion. And it was something, again, totally out of this world. And the other cool paper that we picked up just recently is actually the largest number of lightning strikes ever recorded within an hour. That far exceeded anything else that's ever been reported by any event. So just in terms of the explosion itself, forget the textbooks, just really was world leading in many scenarios. Oh, wrong way. And this is actually a nice video taken by a Navy officer. Now I saw this and I thought, oh, that's strange. What are those two islands there? They're not islands. They're actually tsunami waves traveling towards Tonga. And you can actually see what I mean. So these aren't, forget your pictures of the Japan wave. That's this big long wave that's kilometres long coming across. These are very, very well-defined, very, very high wave features that were travelling at high speed. So this is in the near field. Very, very bizarre behaviour for the waves, and it's making fun for the scientists and modelers to try to reproduce actually what happened to that event that actually caused waves like this. In terms of the Tonga itself, we can't forget that at the end of the day, it's a tragedy for Tonga. It says 4 deaths. There's now been a subsequent death now that's now being linked to the eruption. That's now 4 people dead in Tonga. 80% of the population impacted by the eruption. Underwater communications were cut, and that's huge because it means no one can actually call in and out and find out what's going on, what help is needed. For an island, Pacific island like Tonga, that's a very significant problem. Crops, livestock, freshwater fisheries badly impacted, not just from the tsunami, but also from the ash fallout. And there were big questions at the time about what's the effect that ash does on drinking water or livestock eating it. Now, is it going to be some toxic effect from the metals within the ash? And we know now, well, we think now that there's actually probably no long-term effects because of that ash fall, but we don't actually know. And the cost is huge. Nearly 20% of the GDP was in damages for just this one single event. Right, going back to our mission to go and find out what happened to this volcanic eruption. Why did it do this? So this is a map that we drew about 2 weeks after the eruption when scientists decided we need to get there fast to find out what actually happened. And this is all we knew. So we have a bathymetry map of this island, of the seafloor, and we realised that all the evidence about what happened that day lies underwater. So we have to do a full scientific marine survey. The only information we really did have is that the communication cables were cut. So you see on this slide here, you've got the white line going north-south, that's the domestic optic fibre cable, and you have the east-west line, that's the international optic fibre cable that joins Tonga to the rest of the world, and those yellow dots represent where the broken pieces of the cable were found. So they were shattered between those yellow crosses. And what I like to point out is this point here, where this one here actually doesn't lie on the laid route. So these lines actually in the cable as laid. This broken end here was found 5 kilometres to the north. So just look at this, we can easily tell that whatever happened underwater in terms of volcanic eruption affected this whole area. 6,000 square kilometres of seafloor had to be affected by this eruption. And again, we couldn't really explain what happened here. The working theory at the time we were sailing was, how can you explain such a big explosion? The most likely scenario is probably some sort of sector collapse. Think Mount St. Helens exposed the magma chamber to the sea, and that could explain the eruption. And the working theory in here was that there would be some sort of sympathetic avalanche, probably off this volcano here, or this volcano, more likely because it's gone north, that's caused it. There's there was a 5.5 magnitude earthquake associated with this eruption, so maybe it dislodged some material, caused an underwater landslide that worked it. So this is our working area that we decided to survey. This line here represents the no-go zone for our research vessel. We decided, management decided that it wasn't worth the risk trying to send humans back into that. We didn't know the mountain was going to erupt again. We had no idea. We knew it was underwater, but we didn't know how far underwater it was. And water depth does make a difference in terms of the risk. And this is because underwater all volcanoes are powered by gas. And if it's an underwater volcano, that gas goes into the water and it lowers the density of water. And it's a fun fact that steel boats do not float in low densities. So we did not want the boat to go over the site of the explosion. We had to stay on the flanks because we didn't want to lose the boat. And this is not a risk that we kind of guessed through modelling. And this is a good example that the Japanese and NIWA actually did about looking at underwater eruptions. So this is just a simulation of under eruption, a little bit of gas, but if you look how much water gets displaced on the surface, if you were a boat sailing anywhere near that, you would have been in a lot of trouble. Now, this actual research that we're doing for NIWA in Japan was actually looking at tsunamis generated by underwater eruptions. It wasn't about the risks of boating, but I think it's a good analogy about why we couldn't sail Tonga over the top of the volcano. And there is actually a couple of case points where this is not a good idea. Probably the most famous is this particular ship, the Kaio Maru number 5, 1952. It was sent to investigate an underwater eruption, and basically the mountain erupted and it disappeared with all hands. That explosion you see there on the picture, that's not actually the one that sunk the ship. But it was there 1 minute, and an enabling vessel just basically the seas opened up and it just sunk with all hands, and we didn't really want to have the same thing happen to the Tonga. So, given that we couldn't get into the crater itself, we decided to really work those 6,000 square kilometres around the around the flanks of the volcano. These are the sort of instruments we use. We use the multi-beam mapping system that uses 3D maps of the seafloor. We use this DETIS, the deep towed imaging system, which is a towed camera system, takes still photos and videos on the seafloor. We did a lot of oceanic research. That's called a CTD, which is a conductivity and depth probe, which is on the bottom of the instrument. And these are water bottles, rosette water bottles on the outside that are designed to collect water samples at various depths. Again, we're looking at the impacts of the ash fall on the oceanography. This is a freshwater, this is a trace metal pump, I should say. We're trying to take trace metals from the ash. And we had a multi-core push-core system that we used to sample the sediments on the seafloor. And here it is retrieving some samples. Now, we couldn't get the big boat into the caldera, so the plan was to deploy oceanic gliders. And this is the oceanic glider here. So it's a robot. We don't mind losing 2 or 3 of those. So we deployed that with the hopes of getting into the caldera itself and taking samples. It failed, which is unfortunate. We got a couple of samples inside the caldera, but it turns out that these sort of gliders don't like tropical water temperatures over 30 degrees, and the vacuum pump failed, and we didn't have much luck with the gliders. But we did have this. This is cool. This is part 2 of our voyage. This is what's known as an uncrewed surface vessel. It's a USV Max Lima, 12 metres long. It has a multi-beam system on board. It's called an uncrewed surface vessel, not unmanned. And the reason it's called uncrewed is because it actually is rated to carry passengers, but the people driving the boat aren't actually on it. The people driving the boat were actually sitting in Essex in the UK. And so I've actually been to their control panel. They still have a steering wheel for the boat. They've got the radar and all the other instrumentations you expect to see, depth sounders. But it was actually steered live from the UK. So it's not a robot. It's not an autonomous vessel. It's not pre-programmed. It's actually steered live. And then you had scientists coming in, and they were taking in 24-hour watches, manning all the scientific instruments. And I was part of the science crew, and it's quite cool. I was sitting in my lazy boy chair in Seatoon, and I'll be on WhatsApp to the skipper saying, "Oh, there's something really interesting on the port side. Can you turn the boat around? We zap it." We had that level of control remotely for a boat operating in Tonga. And I have to say, this is probably how marine science is going to look in the future. I think we're going to see more and more of these uncrewed surface vessels doing work, and scientist jobs actually going to be more and more relegated to sitting in your office controlling instruments. And this is an operation. You can actually see Hunga Tonga Hunga Ha'apai Islands in the background. This is returning from a mission. This is taken from a patrol vessel. It has no mothership. So a lot of vessels have motherships. This one has no mothership. It just happened to be a boat that we chartered to take film for videography. But these sort of uncrewed surface vessels are fully, you can let them run, and you don't need to have any other on-the-water assets out there doing their work. And this little picture on the left, you can see, this is a little app I had on my cell phone. I can sit there in real time, see where the boat is. I can actually change instrumentation to see real-time cameras, or what the waterfall display is, or what the multi-beam was, and I can control literally everything from my iPhone. It's pretty amazing technology. And we use this to fill in that gap in the hole where the volcano used to be. So let's look at the results. So in colour, we can actually see all the mapping we did on the Tonga, which is a traditional vessel. We've included the part that the uncrewed surface vessel has done before. And if we look at some of in terms of what we concentrated on, we really concentrated on the edifice itself, HTHH edifice itself. We concentrated on the domestic cable, try and find out why that broke, and that section of the international cable, east-west, try and understand why that broke. And you can also see we also ran some lines running down to the southwest and out to the northeast. And the part of the plan was we wanted to understand the isopack thickness of the ash. We had some really good samples and ash thicknesses recorded on Tonga Tapu. All the rest of the airborne ash would have gone into the water. So we actually ran these lines to actually try and get a nicer pack map of airfall distribution. That was the theory. In terms of before and after pictures, this volcano was not particularly unusual, but in 2017, there was an American vessel called the Thomas Thompson that was actually working in the Lower Basin, and it had an equipment failure. And so it was coming into port to get some parts, and it had too much time in its hands, could only approach the port in daylight. It had about 12 hours to waste. So they said, what do we do? So I said, well, let's just map this particular volcano that was completely uninteresting. So in 2017, they actually mapped the volcano, and that allowed us to have a before picture. We then last year did an after picture, and the benefit of that before and after is it gives us completely a really good understanding about what happened that day. We can actually do the direct comparison. When you looked at the profiles in the top picture, again, remember we talked about when we were going out in the voyage to start with, the working scenario that everyone was working on was a septic collapse exposed in the magnet chamber. When you look at the edifice itself, it almost looks completely unchanged. I mean, there's very, very little difference on the flanks, on the sides of the volcano. The only dramatic difference is there's now a giant hole where there never used to be. And I can't really stress how big that hole is. It's 850 meters deep. It used to be a volcano 120 meters high, so it's lost nearly a kilometer of height. And that hole is so big that you could actually put the Naurahoe edifice, if you look at Naurahoe from State Highway 1, you can shove that inside that hole and be still underwater. That's a really large hole. If we zoom in to the volcano itself, we can see that very large hole. Obviously, there's not really too much obvious damage or change in the shape of the seafloor because of this truly massive eruption. But there are a couple of things that are really obvious out the get-go. There's some very, very subtle gullies that weren't there before. And so they weren't there in the before picture, they're there now. So we immediately interpret those as pyroclastic density current channels, areas that were scoured out from planian cloud collapses from the eruption. And the other thing, we noticed straight away is way up deep. You can see right at the very, very top here, actually some very, very large sediment waves. Now, those sediment waves were there in the before picture, but in the after picture, you can see that they're quite clearly different. So we immediately surmised that there was some significant pyroclastic flow activity happening because of this eruption. And actually, just looking at the bathymetry, we can track it to at least 30 kilometres away. But the power of actually what happened comes when if you take away the before picture from the after picture, and you get an image like this. So areas of seafloor losses in the blue, areas of seafloor gains in the red, and instantly can tell you quite instant that there's actually some very significant pyroclastic density current activity happening all the way down the flanks. So in the blue, huge amounts of scale coming down. This particularly big dark blue one you see here, that had seafloor loss of nearly 150 meters high. 148 meters of material was excavated down that X section there. That very dark red lozenge and the top there, that's over 85 meters of new material is added to it. So we can instantly see there was actually some dramatic pyroclastic density currents that happened, most likely during collapse of the planian cloud. We can't answer, is it partial collapses and multiple pulses of pyroclastic density currents, or is there a complete column collapse and they just rated out? We actually can't answer that timing. That's sort of the work that's still ongoing, but we can say that column collapse generated pyroclastic density currents that have eroded vast amounts of material and have deposited a lot. And in terms of the volume calculations, just what you see here, and again, this is only this, we can only do this map where you have overlap between the before and after picture. We've mapped more than that, but we never had the before picture to do the calculations. But just in this area, we can see 9.5 cubic kilometers of material. Sorry, I've got that reversed. 9.5 cubic kilometers is being lost, blown away. Of which, so that's nearly 10 kilometers of erupted material. That's a hell of a lot. I mean, it's 22 Wellington harbours worth of volume. That's being exploded away, of which we can track 6.7 cubic kilometres. So there's still about 3 cubic kilometres unexplained. Now, there's papers that are just being published that estimate about 1.5 cubic kilometres went into the atmosphere. So there's still 2 cubic kilometres of material, which is a vast amount of material that's even outside of this picture. So the majority of that loss is from the hole in the center, the crater itself. 6 cubic kilometers of material was exploded just from the crater itself. But significant amount of stuff was then subsequently lost as that Plinian cloud collapsed and created these really dense density currents and just basically plowed away and scoured out the flanks to create these channels. And this is quite a complex map, but I'll try and explain what we're looking at here. Those black lines, those back squiggly lines, is actually the modelling we did after the event, saying, let's model a column collapse and see where those pyroclastic density flows current went. So they are direct modelled currents flowing out. And actually, we know that those models actually track really well with what we see of the loss diagram. So we think the model's pretty good. But what I'm going to draw your attention to is this light blue dot down here and the bottom left. This is 80 kilometres as a crow flies from the volcano. And this is a core that we retrieved from the site. And what we found is we found pre-eruption deposits. We got 70 metres of core. The bottom 40 odd centimetres is old seafloor. And then you have 25 centimetres of pyroclastic density current. It's beautiful, fine grains, medium grains, lovely flow structures coming through. And then you have about 2 centimetres air for ash on top. So what this tells us is even 80 kilometres away, you're still generating 25 centimetres of pyroclastic flow going there. And put things in the context. What do we know about submarine pyroclastic flows? They've only been documented really twice. Most of my documentation happened at Montserrat volcano. And the difference with that particular event was that Montserrat has pyroclastic flows from dome collapse. So the pyroclastic flows subaerial, that then subsequently went underwater, and they went the staggering distance of 650 metres. And then we had this, and we're still finding 80 kilometres away as a crow flies, 25 centimetres of material flowing out there. What generates that level of, what do you need to generate that level of power for material to travel that fast, given that there's actually the density differential between water and the currents is much closer than air and the currents. On land, we can get pyroclastic flows going a long way because air is a lot less dense. This is underwater. So how much power must have been, or flux must have been in those flows to actually push those flows that far? Now, we have anecdotal evidence that some of those pyroclastic flows might have gone over 120 kilometres away. That's something that we've still got to confirm, but we actually have evidence that these things just flowed and flowed and flowed. And what's more, we can actually see that these flows not only flowed down the slope, but actually had enough power to go up over ridges and morphological highs into subsequent valley systems and just keep going. They went in that direction and they didn't stop regardless of what the downslope was. A lot of power happened. And there's some actually really good work from Mike Blair from National Oceanographic Centre in the UK. He's done some timings. He was responsible for, he was paid by the cable company to work out what happened to their cables. We have various timings of those eruptions, and we have exact timings when those cables broke. And what we discovered is that the domestic cable here, which is this dashed line that broke here, the speed of the pyroclastic density current to break this was between 70 and 112 kilometres an hour underwater. And that's in a Nature paper that's about to be published. That far exceeds even the fastest pyroclastic, fastest turbidity current ever recorded. I mean, it's just a staggering amount of energy that's gone through there. This cable breakdown here, if there was a pyroclastic density current, we'll talk about that, you're still getting speeds of nearly 50 kilometres an hour to break that. And those timings are just based purely on, we know exactly what time the Big Bang happened, so we know exactly what time those cables broke. And based on the modelling to give us a flow path, you get those numbers. It's a pretty staggering result. So let's talk about this, go back to the cable. Let's talk about what actually happened here. We haven't explained why this cable was found 5 kilometres north. We explained what happened here. Simply put, it got buried by 30 metres of material from basically a massive pyroclastic density current that extended all the way north. This valley here, to get here, you had to go through 1, 2, this is the 3rd valley system along. And again, we don't know what's going on, but the bathymetry didn't give us a good answer because the bathymetry resolution between the systems wasn't great enough to show whether there's any change in the seafloor, but the backscatter bathymetry gave us a great result. So backscatter, so when you echo sound, you send out a pulse of sound at a certain power level and listen for the echo. And if you measure that power level, the return power level of the echo, that's called backscatter. So the stronger the echo, the harder the seafloor, or the stronger the reflector, and the softer the echo, the softer the seafloor, or the softer the echo. And this allows us to give this map here. So light areas in here is areas of low reactivity, so it's probably soft muds or fine sands, and the hard areas are rocks. So what we see here, we look at this section here, you have volcano 3 up here, and you see the flanks of volcano 3 with its lava flows coming down the sides. This is volcano 1 here, and so you have the flanks of volcano 1 down here. No evidence of avalanches to explain it, but what we do see through the backscatter is this really cool little this little sine wave that comes through like this, and then you see these new sediment waves coming through. So that tells us that actually there must have been a flow that's come through here, and it's actually broken the cable, and as this wave is swinging back to the north, it's taken that broken cable north and it's deposited. So we haven't confirmed this, but the likely scenario for the international cable is the pyroclastic flows went into 3 valley systems over 3 ridges into the system, sloshed between these 2 other volcanoes, broke it. We've got timings for this. If this happened, this is about still 50 kilometers an hour, and deposited the end 5 kilometers north. Geologists in the room talk about rocks. We got lots of rock samples, and that's really critical that we did that. But most of the rock samples we found were andesites. We did find some porphyritic basalts, some of them with some pretty cool olivine crystals in them. We found a whole bunch of pumice, which is not surprising, but we found some rhyolitic or silicic pumice, which is obviously rafted, but we still managed to pick it up. We found some tonalite, which is really cool. It really gives a good indication about sort of activities and under the crust that produces those sort of rocks. And my coolest thing I ever found was some Pellé's tears. And that was cool because I found them 7 kilometers away from the nearest land and 400 meters underwater, and they were completely unweathered by the water. So my interpretation for these Pelé tears were they were actually in place subaerially on one of the islands. And as the island was literally blasted away by this column collapse, it's pushed these Pellé's tears underwater, and we managed to retrieve them. Some key messages basically. So we did a lot of mapping. The edifice is still intact, but we see evidence of many pyroclastic density currents. Remove 50 kilometers an hour, we can actually prove it to 80 now. We have evidence to extend, evidence to suggest we could probably track that to over 120 kilometers away. And we're talking about nearly 10 cubic kilometers of material was erupted from the volcano. We're going to look at some further work. This is some camera work, which features some interesting parts on the seafloor. This is there's no biologists in the room, is there? Before I start saying bad things about biologists, no? Okay, just checking. The biologists, they love things that live on the rocks. So what they're really interested in is what is the effect of this volcano on things living on the seafloor. And it's what you see in these lovely pie charts. These pie charts, the bigger the pie chart, the more animals they found, and the more colors there are, the healthier the ecosystem was. And a black X means we examine the seafloor. And when I say examine, we did 3 or 4 hours of videos just going along, and we saw nothing. And you can see there's lots of places where we saw absolutely nothing. Now, the cool thing about this is actually right even on the flanks of the volcano, we actually found a site where there was life still living. I just showed you the map that many cubic kilometers of material was wiped out by pyroclastic density currents. There's a spot here where life is still alive. It was pretty sick, but it still survived, and that really surprised us. But what was interesting is these big spots here that you see, the big ones, are actually the summits of other volcanoes in the Tofua volcanic arc. And they were healthy, amazing. In actual fact, they showed very little evidence of such a violent eruption. And that tells us that all that volcanic material just hugged the seafloor. Very little effects from the stratospheric ash. In fact, on the top of the volcanoes, we didn't see any evidence of any stratospheric ash whatsoever on them. They were completely untouched. So it's really interesting how localized the airfall ash was, but how channelized the pyroclastic flows were. So I'm just going to run a video here. This video is going to take us down. Now, remember when I talked about there was a really deep channel out to the northwest that was eroded nearly 100 80 meters deep. This is the video down that channel. Now, so what we're seeing here is just still lots of fines that we're interpreting as the fines from the pyroclastic density currents that have settled last. You can still see huge areas of basically bedrock that is being ripped up. And again, this tells us the evidence that, you know, these aren't chunks. This is actually bedrock that's been completely ripped up. So we think that it was a very dense, turbid current that flowed through there, and it just plowed its way through. This second shot is from another channel just around the corner where over 80 meters was added. What we're seeing, we're not seeing any bedrock at all. We're actually just seeing this beautiful fine seafloor. These are fine sediments to fine sands to muds. The sample is a few centimeters of airborne ash, but the rest of it is actually hot parts of pyroclastic density currents. Same distance away from the volcano, both of them are effectively in channels, but it's obviously different hydrological mechanisms that have happened on these two events. And let's compare this with what the seafloor should look like. This is the summit of Volcano 3. Now, Volcano 3, interestingly, erupted in 2007. This is the summit. So all this life, which is a healthy, typical sea life, has grown since 2007. But you're not seeing those fine sediments. You're not seeing even evidence of atmospheric ash there. And we saw from those pie charts, this is actually completely a very healthy ecosystem. And we can see again, don't forget this is only 30 kilometres away, so incredible fish species. If you look at the seafloor, the biologists got very excited because they see holes in the ground, and apparently it means critters live in there, and it's a healthy ecosystem. Completely unaffected from the volcano, less than 30 kilometres away, yet other places still it's just nothing but desert. And just as an aside too, the only part of the whole Tofura arc that was really being examined before was Volcano A. I mentioned it. It's famous because the Germans discovered on a sonar vessel, they discovered in 2003 a hydrothermal seat system that has these Bathymotus muscle beds on them. And so that was actually something that had been really well studied in the past. And it gave us a good opportunity to study it again, just to see if these really sensitive ecosystems had been affected by the volcano, and we found zero effect for them. And so that was actually good news for these particular beds, but it also gives us a good indication about how limited this volcanic eruption was spatially. You know, everywhere we looked, the evidence suggests that all the energy went straight up in the air, very little went sideways. So these just going to skipping through. So we're talking about this slide is actually about, we're looking at the cores, those push cores we did. The biologists really were interested in what critters lived in the sediments. But I'm going to skip over that biology part of it. And these are the push core sites. I'm going to talk about some good examples. Here's an example of a push core that was some 50 kilometres away. This is not the same as the sediment we showed 80 kilometres away. But again, you can see the original seafloor very clearly, that black band. And then you have a graded pyroclastic density current that goes nearly a metre high. And that's 50 kilometres away. In contrast to a push core that was done much closer to Tonga Island itself, we're not getting any fines in that at all. We're getting really coarse atmospheric ash sediment that came through. This isn't pyroclastic density current. This is quite clearly airborne ash that's consolidated down, and it's 30-40 centimetres thick. So we're actually seeing some quite spatial variations in terms of sediments on the seafloor. And this map shows, what I'm trying to show here is, this colour map that you see here is the modelling about the pyroclastic density currents, just to give an indication about where they flowed. And I've overlaid that over the places where biology was found. And this just proves the point that biology only ever existed where the pyroclastic density currents didn't go. And this, I know it's modelling, but it actually really reinforces what we observe in situ, that in terms of the seafloor and the energy and then materials that came from this volcanic eruption, it all generated as pyroclastic density currents that just flowed tens and tens of kilometres. Just in terms of the biology mapping, little sign of animal life in the flanks, we saw that. We did find abundant patches of benthos and ecosystems that survived the eruption and neighbouring seamounts. So our working hypothesis is that these seamounts effectively act as pipuka, as refugia from volcanic eruptions. And this is important for the future management of this event and other events in places like Tonga, is that you can still have a major event like this, but there's actually a very close source of genetic biological material that could help repopulate those areas. And that's important for the people like the fishermen and the coastal communities that really rely on seafloor life for their subsistence. I'm going to touch now about some other work we did about the ash. You can actually see here, ignore the pretty picture of the lovely Circe and eruption, but the discoloration in the water, and all that water really affects, all that water is caused by ash and material into the ocean and chemicals. And what we discovered pretty quickly is if we looked at the chlorophyll, which is a phytoplankton, before and after, we actually see that this material that landed into the ocean generated, well, it could be argued it generated very large plankton blooms. So airborne ash is a nutrient to life in the water. Like the first thing it does, it generated this big bloom of plankton. And so we actually checked that out by using our CTDs and water bottles. And one of the unintended consequences, I'm going to bring back geology here, is we put a GoPro on this camera, and we were trying to find evidence of this phytoplankton bloom. But when we looked at the GoPro footage, we found this. So we're sending through the clear tropical waters of Tonga, beautiful visibility. And then at about 200 meters deep, we will hit patience. Okay, we're getting into the dark depths now. Lost the light zone. Thank you. We found this. I call it a London fog. It's like literally going through a pea soup fog. And we saw strange things happening in the CTD. Dissolved oxygen was down, the transmission, beam transmission was down. So instruments are saying something was happening at 200 meters deep. Once you push past 250 meters deep, the water cleared up and everything disappeared. So something was in the water column around the volcano at 200 meters deep. Now this confused us because according to all the laws in terms of the ash fall that landed on the water, it should be sitting at about 1,500 meters deep in terms of its density. And we did see evidence that the airborne ash hasn't quite reached the seafloor yet. It's still settling. Most of the ash layer is sitting at about 1,500 meters deep, not 200 meters deep. So something else is generating this material around the volcano at 200 meters deep. And when you analyze that at the microscope, what we're seeing is volcanic glass. So that fog is actually shards of volcanic glass. So quite clearly, this is volcanic in origin. It's not from the airborne ash. So what's it from? And when we looked at this layer, and again, we've got Hunga Tonga volcano on the left, and we're going away from it in distance, we can actually see it's a very horizontal band. It's always at the same height, but it's concentrated closest to the volcano. So the obvious implication was the volcano is still erupting. There's still fresh glass production happening. Well, there's still glass production happening in the volcano itself. The million-dollar question is it hydrothermal vent systems recirculating old glass, or was it actually fresh magma being produced and fresh glass being produced from ongoing activities? And kind of to answer this, going back to the uncrewed surface vessel that filled in this hole, we looked at uncrewed surface vessel into the acoustics. We can actually see a lovely new cone growing. This is not the same site that erupted. This is a new site. It's really close to Hunga Ha'apai volcano. And you can see quite clearly multiple flares of material happening. So our working theory is there's still big post-bang volcanic eruption still happening now. And the glasses we are seeing in the ocean at 200 meters deep is actually glass from new lava production. And that has huge implications about, is this a new island going to grow? The volcano is still very clearly active. And in fact, when we looked at the whole caldera itself, we actually found many sites where the volcano is still actually erupting and producing fresh glasses. And there's actually some really good work that Pernell de Ron's done. Pernell had a unit on the uncrewed surface vessel that looked at the oxygen reduction potential that was actually used to analyse those gases. And he's got some great work done. He's presented them at a couple of posters, trying to really explain what's happening in terms of the gas chemistry, and there's some really weird stuff going on. I don't begin to understand it, but basically one side of the volcano is very sulfur rich, that's erupting into the water, and the other side of the volcano is very sulfur poor erupting into the water. So again, there's something really dynamic happening, and the magma system still happening on the magma system under the volcano. And that's kind of where we're at now. We still have a few papers to publish. We've got more core results coming back in. We're doing some more collaboration. There happened to be an American research festival happening in Lower Basin that accidentally collected a lot of geological data. It was a biological cruise. So there's still a lot more work happening. Our current plans for the future is we've got a proposal to do more ship time next year, follow up, see if this new cone is growing, and just see what's happened to the volcano now. Is there still ash in the seafloor? And the biologists also very excited too, because they really want to know, what's the biology returning. Actually, this is my last slide, but I will bring them to another topic. I had gotten a bit of an argument with Shane Cronin, actually. Shane has always advocated that he's always called this a caldera, and he's talked about, this is his mechanism for explaining the Big Bang is that as the caldera collapsed, the water got into the magma chamber, went bang. But I mean, for me as a morphologist, for it to be called a caldera, I really need to see some ring faulting or some sort of evidence that some sort of collapse happened. And I'm just not seeing it here. I actually interpret this as actually an explosion crater, just a very, very large explosion crater. And I'm looking at the audience here. If anyone's got any opinions, one or the other, and please correct me, but all the papers published up to now call this a caldera. I really don't see that. I actually see this as just a very, very large explosion crater. And part of the evidence that came out from Emily Lane's tsunami modelling is she tried to explain how the waves landing on Tongatapu, and she modelled it different mechanisms, including caldera collapse. And the waves generated from caldera collapse did not match the waves observed. And interestingly, the wave that if there was a large explosion, that perfectly mimicked the wave that we actually experienced. So I know it's not really evidence to suggest this is actually an explosion pit, but that's anecdotal evidence. It's kind of helping support the fact that there actually was no caldera collapse in this particular eruption. It was just a big bang. Magma chambers exposed to water through smaller bangs, exposing a little bit more. But again, I'm totally up to people to say, no, you're full of shit. Can I say that? No. So, but anyway, that's my theory anyway, and that kind of says where we got up to now. And I'm happy to take any questions.
Thanks very much, Kevin. That's an amazing talk, amazing science and amazing observations that you guys have made up around that Hunga volcano eruption. So we've got any questions from the audience here or online?
Just around online,
yeah.
Pyroclastic flows on land have very high temperatures, I think. What happens when they're underwater? Do they cool right down?
I hope this is on. The answer is we actually generally have no idea. So it's never been seen before, and we actually have no measure of that. But before we can look at, one of the things we're looking at is, I showed a quick slide about creepy crawlies that live on the seafloor, and if we can look at those creepy crawlies at that layer where the old seafloor was overlain by pyroclastic density current, if they're effectively cooked, they'll give indications of heat, but we're not seeing that. So again, we're talking about the mechanisms on land. Pyroclastic flows on land travel so far is because air is much less dense than the density of the rocks. Underwater, water density is so much more than air. So why are these flows going so far? Now, one of the mechanisms could be heat, and one of the working theories that we can't prove is that as these super hot rocks descend to the seafloor, they create effectively an envelope of steam that's kind of self-seals these flows. And that could explain certainly the first part of that flow, that let them accelerate. There's no evidence. This is just pure conjecture about that.
Kevin, I would have thought if the pyroclastic collapse, the eruption collapse enters the water column, with those volumes and densities expected, there's no reason why those flows wouldn't cascade into turbidity currents that would flow for many hundreds of kilometres.
Yeah, that's exactly right. Yeah. So
why would they not?
Why would they not? And it's purely because of the density of the column in the first place. And it had all the potential energy when it went up in the air, and especially if you're talking about columns that were 56 kilometres high. or even 20 kilometres are high. That's a lot of potential energy. If it all comes crashing down, 9.5 cubic kilometres, that's a lot of kinetic energy that's just scouring its way out, and it's just going to go. And so I don't think you need to get the heat into it. I don't think the heat, I suspect that probably cools really quickly. I don't think heat's actually going to be a strong driver in making those flows go. I mean, we don't see them in turbidity currents. You don't need them for those turbidity currents at all.
Cool. Let's check the chat online and see if there's any questions here.
May I have a question? May I have a question? Thank you for your sharing of your research. And I'm a geologist, so I'm really interested in the geologic mechanic and the structure of this area. So I have two questions. The first one is, as far, do we have some research or research about the structure, formation structure, or seismic section or geologic section of this area of the formation? So, according to this, maybe we can know the geologic mechanism of the volcano, this volcano. And the second question is, after this volcano, do some organized or countries have the follow-up research of monitoring or about the seismic or volcanoes? For example, do some organized put some seismic sensors or some EOS monitoring services about that? Thank you.
Yeah, there's a couple of really great questions. The first thing, a question about what we knew structurally about this volcano was nothing. It's before this eruption happened on January the 15th, it wasn't in anybody's radar box. Shane Cronin from University of Auckland, he's done some work for several years on the geology and the sort of the nature of the rocks. But in terms of the marine science, it was actually something that was actively avoided. If you look at all the historical surveys, no marine geologist ever expressed any interest in this particular volcano. They were always looking at other places for reasons I'm not sure why. Certainly, there's been no seismics of it. Any of those, as far as I know, any of those volcanics have ever had seismics on them, and that's a shame. So, our cunning plan for next year is we'll be running multi-channel seismics over that to answer exactly that question, because the critical thing for Tonga is if this volcano's acted like this, what's to say any one of the others along Taufua isn't going to do the same thing? And that's a very real risk they need to address. Now, in answer to your second question, in terms of other countries, the biggest country that's really taken interest in this is Japan. And so Jamstack was one of our collaborators, and they've really taken this sort of lesson on board, and they're really looking at how they wire up how they monitor and instrument their submarine volcanics, and actually because they've realised that it really has been paid attention to. So I think there is lessons learned. Japan's taken it on board, but places like, there's the nearest OBS really in ocean, the seismograph in Tonga is in Fiji, and that's it. Countries like that really should be paying attention to instrumentation just can't afford to do that. And it's just, in this case, this is a fatal mistake. So I think what will happen in the future, especially Tonga, will suddenly get a lot of foreign aid to really instrument up their volcanics a lot better to try and have a better prediction on this.
Cool. Okay, thank you very much. Thank you.
My question?
Yeah, how does this compare with, say, the 2012 eruption from Harbour Sea?
Well, the different volcanoes, it's hard to say because Harbour never breached the surface. So
some papers suggest it did.
I'm looking at other people here. I'm not aware of that. If it did, no one detected it.
Because it was pink pumice.
Yes.
Like the pumice on the surface, but the eruption, and that's the thing, that's the critical, the water depth. My understanding, correct me if I'm wrong, looking at other people in the audience, that Harbour is really deep.
Yeah.
And this scale of eruption, if it happened in Harbour, you would have created a bubble maybe 1 or 2 kilometers, maybe a kilometre up, and then it just wouldn't have gone any further. It just, the surface, you wouldn't have seen any on the surface. You'll see floating material, but that eruption power, pressure, would have been contained by water pressure.
Was something, there was almost evidence of plume from high.
An aerosol plume.
Yes,
Okay. Yeah.
that it actually punched through 700 meters of sea.
Right. Yeah. It's quite deep in it.
It's
Harbour.
deep, yeah, it's
It's really deep. That's impressive that it did that. I should talk to people find it. But again, it's hard to measure that and compare it because this one was almost atmospheric. Like the atmospheric measurements we got that were outstanding, and we can get some amazing, 65 megatons. That was 65 megatons of explosion. I mean, it was a big bang. And Harbour could have done 65 megatons, but it's underwater and most of the energy we just don't know about. So it's really hard to make that comparison.
Flows went a long way.
Yeah, it's a silicic volcano though, right? So the lavas are quite different. And it's just sort of, Harbour exploded like we expect a silicic volcano to explode, whereas this is a baso-andesite volcano that exploded almost like a silicic volcano. And that's the difference. Yeah.
Cool. Any other questions? Great. Thank you. I'd like all of you to join me in thanking Kevin for an absolutely fantastic talk. I'm here all night. And I guess we've still got an open talk schedule. We haven't got any talks scheduled at the moment for June and July. So, if you want to put your hands up or you've got some colleagues you want to put up for talks, we'd be very keen to hear from you. So please let me know, scottnotter@niwa.co.nz, if you're keen on giving a talk. We want to keep the branch going. We want to keep these talks as functioning as we can over the year. And if we don't have people actually putting their hands up, then these talks will disappear, unfortunately. So, we need you guys to be active in the community. So spread the word amongst all the members. We've got 200 odd members here in Wellington. Some of you might want to give a talk, promote your science, get it out there. So thanks very much. Thanks for coming along.